Hello, have you been faced by data that looks like this? You take a look at it, you think, okay, it's not linear, it doesn't look like it's going to fit a line. Well, it looks like it's curved, it goes through 0, 0. This is great. I know some things I can write about with regards to this data. You know, you can say it's curved, you can say it goes through 0, 0. I can say that y is increasing more quickly, it looks like, as x gets bigger. And then you come to the question, do I go ahead and say that this is in fact a relationship that is exponential? Is that appropriate? Well, a lot of you have been faced by this question. Let's go ahead and take a little bit closer look at that. First, let's go ahead and take a look at the comparison between a curve that looks like y equals x squared, and this would include other versions of this equation where it's y equals ax squared. It really wouldn't change much to have that constant before the x squared. And secondly, let's go ahead and compare that to a curve which is like y equals 2 to the x. So I've already graphed for you y equals x squared. You can see the data is here, and I have the curve down below. Let's look to see how y equals 2 to the x compares. So when x equals 0, you have 2 to the 0, and that's 1, that kind of special case. Let's take a look at the other ones. So if I put in x equals 1, that's y equals 2 to the first, that's 2. You can start to see the curve building down here. So I've got the next point. Okay, for the next one, this is now y equals 2 squared. Okay, that's 4. Y equals 2 cubed. Y equals 2 to the fourth. Let's pause for a moment and take a look at the curve so far. Looks like it's pretty much matching the quadratic. Okay, y equals 2 to the fifth, so 2 times 2 times 2 times 2 times 2. Hope I got enough there. Oh, it's 32. Okay. 6, y equals, that was y equals 2 to the sixth. Take a look at the curve now and what's happening. Let's finish that out. 7th, y equals 2 to the 8th, y equals 2 to the ninth is even off, and y equals 2 to the 10th is way off of our graph. You can see now it's 10 times larger than the other one. Look at how dramatically that curve grew in comparison to the quadratic relationship. Okay, so which of these likely fit the data that you've had so far? Let's take a look at some sample data. There's a decent chance that you have had data that looks like the data here with these triangles. If you go ahead and you try to fit this with an exponential fit, there's a good chance that it will fit immediately at the beginning, but that it may well diverge later on. If you try to make it fit later on by adding a constant, in other words, where you'd have y equals a constant times 2 to the x, or y equals 3 to the x, or y equals 4 to the x, you probably will end up with having it fit part of the way along and then not be able to fit the rest of the data. No relationship that we've seen so far this year has curved so quickly as an exponential curve. If, on the other hand, you go to fit it with a quadratic, I'm hoping that it goes ahead and fits pretty reasonably. Of course, there's going to be some data that does not fit quadratic curves, but it's more likely so far. My point, though, is you need to take a look at how the data and the curve fit. If you end up with a 2 to the x or a 3 to the x, then that is an exponential fit. If you end up with something instead where it's x squared, then that's a quadratic fit. And that would include something which is y equals ax squared plus bx plus c. That is also a quadratic fit. To summarize, let's take a look at some things that you might say about your data. 3 different kinds of general relationships that we've seen so far. Y equals ax plus b, or the simpler version, y equals ax. Those are linear relationships. Y equals ax, where there's no plus b, where it goes through the origin. This is also a direct proportion. Quadratic relationships, take a look at those for a moment. Okay. Again, if there's no plus bx plus c, if it's just simply y equals ax squared, so you just have a constant here relating the y and the x squared, that's called a direct proportion. But in this case, y is directly proportional to x squared. Finally, if you end up with a relationship where it's y equals a constant to the x, that is an exponential relationship. Let's save that statement of, hey, y is growing exponentially. Let's save that only for this last case where it's in red. So wait until you find that kind of relationship and then use that statement correctly. Until then, let's go ahead and use statements that look more like it's a quadratic relationship or y is directly proportional to x squared. Thank you so much. I hope this has been helpful. Have a good day.